Welcome to lecture series on digital image processing. Today we'll be starting with the new module wherein we are discussing image segmentation. Basically, we'll try to understand two important features, or we can say characteristics, which are essential in image segmentation, that is point and line detection. So let us see what content we have covered in previous class. In previous class, we have studied different morphological algorithms. I'm talking about the last class wherein we concentrated on three different image processing algorithms, which was related to morphological algorithms. They were like convex hull, then skeleton, then we had seen one method which is called as pruning. So we'll try to revise those methods or algorithm steps, what exactly has happened in convex hull, skeleton and pruning methods. Okay, so whenever we have an image A, and if you say that particular image is said to be convex, if at all straight line segment joining those 2 points considered points in A lies within the area of A, isn't it? That was the general definition for convex, and that's why we consider convex hull as H in a set S. Okay, and we consider it as it is the smallest convex set containing S, isn't it? So if at all you want to set a difference, then we consider it as H minus S. Most of the time we use convex hull for the object description criteria. So basically what we are trying to do in convex hull is iteratively we are applying hit or miss transform to any image A, taking the structure element, any structure element B, isn't it? And we try to union with the A, those structuring elements, and repeatedly we consider the second element of B, like that, isn't it? Continue. So we consider it as B raised to I operation whenever we take up any image. So that's why in one of the example we had seen like what is B1, B2, B3, B4, like raised to the B raised to I, that we have seen for the 4 stages, how structuring element may change for convex hull operation. Second thing we are seen regarding skeleton, wherein we are considering a maximum disk. Okay, and normally maximum disk will be placed at the center of the pixel or skeleton structure, and whenever it touches a boundary of A more than two or more places, we consider that disk as maximum disk in skeleton. So how do you mathematically define a skeleton of A? Okay, so it involves operation of erosion and openings for the skeleton of any image A. So that's why we write it as S of A as union of K equal to 0 to K, Sk of A. So erosion and openings. That's why a skeleton of Sk of A is considered to be erosion operation, then minus erosion operation into that is opening B, isn't it? So where B is considered as a structuring element. So what is A erosion KB indicates, because we are interested in this evaluation. Whenever we consider A erosion KB, it is A erosion B. Again, the result should be eroded by structuring element uh, up to K times. Okay. So till where you have to do that K times operation is a question, isn't it? That's why we consider maximum of K erosion K of A erosion KB is till the empty set you get. Okay, till it is not equal to empty set, you have to consider that K times operation. Iterative steps should be considered. That is the condition. So how to reconstruct a subset using equation is what is this? You have to again dilate. Is a dilation of SK with KB will obviously give the reconstruction of a subset of SK of A, so that we can get the original image. So next we had seen pruning, a terminology wherein we have considered might be when you carry out thinning operation or skeletonization, might be you are having some parasitic component left out in either pre-processing or post-processing, wherein we have to remove those parasitic elements involved in the image, and that is basically done through story. So we have seen one of the example wherein how handwritten characters are affected with extra parasitic elements and how to remove that. So character A was taken for the consideration in the last classroom exam. So we have seen why pruning methods are essential when we carry out thinning and skeletonizing procedures. So let us revise those 4 steps which are used for pruning. One is thinning operation. Second is you have to find the endpoints. Okay, find the endpoints is the second step that you have to carry out in pruning. Third is dilate the endpoint. So dilation operation you have to carry out as a third steps in pruning. And lastly, you have to unite the first step result with third step result. That's why it is X1 and X3. So thinning operation with respect to image A and structuring element, then finding the endpoints, then dilation operation through XOR and intersection of A value, then union of those two results. So today we'll be going ahead with the content related to image segmentation. In block diagram, in the first module, we had seen what are the different steps involved in digital image processing, isn't it? So where we had taken this part as image segmentation. Basically, there we had not gone more in detail, but we tried to understand what is segmentation is, isn't it? So in a very simple sense, if you want to understand what is image segmentation is nothing but you have to divide an image. Okay, you have to divide an image into either component regions or objects. That is what we had seen as a definition for image segmentation. Then even if you divide a particular image into a regions or object, the question arises when to stop for this segmentation, isn't it? So might be what we can say is whenever we are trying to divide an image, you will reach to a situation or application where the objects of interest gets isolated. Okay, till there you should do segmentation procedure. That is what, like, otherwise in a simple sense we can say segmentation should stop when the objects of interest gets isolated. Okay, that's why it is considered as one of the most important step in the analysis of processed image data. Okay, so let's see how on what basis segmentation algorithms are based on. Okay, so we know two basic properties of intensities values. Okay, whenever we have an intensities value, we can consider two basic properties which are related to segmentation. The first one being discontinuity. Okay, first one being discontinuity, second one being similarity. Okay, So try to analyze, because in the next class we are trying to take up the mathematical aspect of segmentation algorithms. Okay, so today we'll try to understand the terms which are involved in image segmentation process, so that the mathematical modeling as well as the theoretical concept related to image segmentation will be very clear. Okay, so in a discontinuity, you are trying to partition an image based on some sharp changes in the intensity. That is one thing you can consider. We'll discuss one this discontinuity and similarity, how they are considered in different segmentation methods. Okay, right now whenever you partition an image based on sharp changes in intensity, it is called the discontinuity. Then when we consider similarity, you have to partition an image into regions that are similar according to some set of predefined criteria. Okay, so when we see this two definition related to discontinuity and similarity, what we can guess? Okay, what we can guess now, like when we consider this, like if you consider this as first category and the similarity as second category, in both the cases we have to assume some boundaries, isn't it? We have to assume some boundaries of regions. Might be they are sufficiently different from each other or similar, like that we have to consider. Okay, but when we consider first case, what I can say is we have to consider for the boundaries of the regions which are sufficiently different from each other. Okay, and from the background to allow the boundary detection. So that is what discontinuity says there. Uh, when we see second, might be we can consider, like we had studied one term which is called as edge-based segmentation, isn't it? So your edge-based segmentation falls into this category. Okay, so edge-based segmentation is the principal approach for the local discontinuity existing in the image. When we consider similarity, that is to partition an image into regions, we had seen several examples. If you remember, some of the examples segmentation might be some animals were there, cat and dog, and some persons moving, like 5 to 6 persons were combined in one picture. Later on they were separated with those edge based and region based segmentation methods. Okay, you can just go back and see even previous notes wherein we had discussed about the edge based and region based segmentation. So, okay, if I consider region-based segmentation approach related to second category, okay, related to second category, which are based on partitioning image into regions that are similar according to some set of predefined criteria. So you can put edge-based segmentation in first one, that is in discontinuity aspect. Approach. Okay, so that's why we say two basic properties of intensity values for the image segmentation is discontinuity and similarity. Are you able to understand? Students, please respond. Okay, so we'll go ahead. For this, some fundamental aspect that is required for an image in a spatial region, because here we are considering an R as a representation for an entire spatial region occupied by an image. Okay, so when we consider segmentation, so it is a process. Okay, it is a process, and we have to now partition R into some n subregions. Okay, here R is divided into some n regions. So that's why that partition can be now renamed with R1, R2, R3 till Rn. Fine. So we are trying to understand what is the spatial region, how it is partitioned, and how those regions are going to behave now what are the properties that region should follow now. Now what we can say, once that R is representing the entire image and that is divided into some n regions, then normally it will follow some rules or some properties, some conditions. What is that? So whatever union of I equal to 1 to n of Ri, whatever regions you have partitioned, if you combine together, you should have that R representation. Obviously that will become true because you are partitioning R in some sub regions. So the union of Ri is R. Okay. Second thing is Ri is connected set. I hope you are remembering what do you mean by connected component, connected set related to a pixel or point. So Ri is a connected set for each I, which is ranging from 1 to n, or even you can start if you are starting with 0. Okay, if you are starting with I equal to 0, 1 to n. Okay. Third condition is Ri and Rj. Means we are speaking of two different regions. When they intersect, it should give an empty for all I and j. So we are assuming that j is not equal to I or I is not equal to j. A fourth condition for the region wherein we are considering for the subset is Q of Ri. Okay, Q of Ri is true. For which value? Yeah, let me continue. I think there was slight problem in network. Students, are you able to hear me? Students, please, one of you respond. Kavya?
Yes, ma'am.
Okay, yeah. Uh, is it audible like a few minutes back? Whether it was the contents were audible to you? 2 minutes back? Kavya?
No, ma'am.
Till where you could listen to me properly? Till where? Till discontinuity and similarity? I hope things were clear. If you have any doubts, please let me know. Otherwise, I'll continue. Okay. So, I was discussing about Q of Rk, which is considered to be a logical predicate defined over some points in Rk. Okay, and as we know, empty set or null set. Normally, we just write 0 slash, or we can say pi type operation representation, isn't it? and union symbols. They represent set union and intersection. These are the two things that are considered in a region. Okay, so we are considering two regions here. One is Ri and the second one is Rj. So how do you say that two regions are adjacent? Okay, we had seen properties of adjacency in module 4 and 2 also. Okay, wherein we had seen N4, N8 and M adjacency in module 2 when we had considered the path length calculation and all, isn't it? So when we have two regions Ri and Rj, they are said to be adjacent if their union forms a connected set. Okay, if their union forms a connected set, then we say that Ri and Rj are adjacent. Okay, if the set formed by the union of two regions, they are not connected, then we call those two regions as disjoint. Okay, we call them as disjoint. So please remember, in image segment these two terminologies are important. One is regions which are called as disjoint and regions which are called as adjacent to each other. Okay, now when we see this first condition, okay, when we see this first condition, it indicates that segmentation must be a complete. Okay, what do you mean by union of I equal to 1 to n Ri equal to R? It should be an complete. What do you mean by it should be an complete process? It is that every pixel must be in a region. That is a condition. So I'm trying to give you a detail of each conditions now. So when we say that according to the first condition, the segmentation must be complete, it indicates that every pixel must be in a region. That's why when we can unite all those Ri, then only we'll get image, isn't it? Complete image. That means every pixel must be in a region. So second condition, okay, second condition requires that points in a region be connected in some predefined sense. Okay. Second condition, when we say connected set, means it should be in a points in a region should be connected in some predefined sense. Okay. So might be you can say that point must be connected, 8 connected, 4 connected, like that. We are talking about that. When you say connected means we are trying to indicate that point must be 8 connected or something like that. Okay. So let's see the implementation or the understanding of third condition. Okay. So when we say now, because just now a few minutes back I have made you realize two terminologies, adjacent and disjoint. Okay. So when we consider this third condition, so according to this, Ri intersection Rj is a null set. Okay. So it means that region must be disjoint. Okay, I hope now the term disjoint is clear. Whenever you are forming the union of two regions and if they are not connected, we call them as disjoint. Okay, so according to this condition, now third condition says that region must be disjoint. Okay, so let's try to understand now fourth condition, which deals with the properties that, see, just check here, q of Ri is equal to true. What it means? So it deals with the properties that must be satisfied by all pixels in a segmented region. So when you write q of Ri equal to true, it means if all pixels in Ri have the same intensity. Okay, please remember, it means that all pixels in Ri have the same intensity. Okay, so let's see the last condition. Okay, last condition is what? Ri union with Rj, which is written false for any adjacent region Ri and Rj. Okay. For a last condition, the condition indicates two adjacent regions. Okay, two adjacent regions. Now we are very sure that Rj and Ri, those two regions are adjacent and must be different in the sense of predicate Q. Okay. So these are the some conditions related to R when we consider it as entire spatial region occupied by the image. I hope all the 5 conditions are clear. Shall we go ahead? So just one example I have taken here just to understand if you apply some different segmentation algorithms, might be you may obtain such kind of image. Okay. Okay. So here we are going for an one segmentation method which is called as the watershed segmentation. How the original image was, and if the gradient image was taken with some edge detection methods. Basically here Sobel edge detection method is carried out, and how the image looks like. And if you have raw watershed segmentation and segmentation using some region markers with the control of over segmentation, how the things may look. Even if you refer, this is for your information. Okay. Last to last year, your seniors have done a project on Sobel operator related to image processing. You just try to find out some project thesis report kept in library, which are based on Sobel operator. Okay. Uh, so that's why this is the one of the area where it can work on image segmentation properties. So one more application related to image segmentation has been highlighted to understand how the things will work. Okay. So here image containing regions of constant intensity is considered for A. Then B, like if you see A, B, C, then D, F. For second image, it is the boundary of inner region. Okay, boundary of inner region obtained from intensity discontinuity is highlighted. And if you consider the result as for the image for segmenting that image into two regions, how the things may look. Then if you go for a textured region, the how the change in image intensity will look. Okay. So just check here. Edge computation. If you are performing edge computation, how image may look like, isn't it? So anyway, you are going to study details of all those, some of the methods. This is only to understand how the image may look when you carry out some different segmentation properties or rule or algorithms on a given image, and how the boundary should be handled for the given image. Okay, and the last one is based on region property. Okay. So some of the basic mathematics understanding is required when we can do either might be point detection, light detection, because we have started with the class wherein I have told we are trying to understand what is point detection and line detection. Before that, we have to understand what is the mathematical aspect related to those pixels involved in image. Okay, and that's why today I'll be trying to give only how the derivatives are used. Might be have not put more mathematical equation in today's class. In notes I have highlighted, but not in a presentation. So once we cover today theoretical aspect, the next class will Of course, it will highlight the mathematical aspects of today's class. Okay. But anyway, in I think either in mass 1, 2, 3, 4, you have studied about derivatives, isn't it? So might be you can utilize those derivatives used either first order or second order. Those derivatives we can use to discover some discontinuities happening in the image. Okay. So what is that? If line is observed within an image, one can consider it as one-dimensional function. Okay, one-dimensional function f of x. Okay, so how to deal with the first derivative? How to deal with the first derivative? So if you take difference between two adjacent fixed pixel, we call it as first derivative. Okay. So how I can say, like if I want to write, like for example, the first derivative is defined as difference between two adjacent pixel. How to consider now derivative? I hope you are aware. Normally you can do, you will write no dy by dx or dou y by dou x, like that you write no. Now for image, if I considering f as a representation or image representation, then I may write it as dou f by dou x. Am I right? So, or else I can, whenever I want to write a derivative, normal method is we write with some f dash of x representation. So what it means? So I said like two adjacent pixel, isn't it? You have to find out the difference between two adjacent pixels. So what are my two adjacent pixel? If I consider it as one term as f of x, what is my next adjacent? F of x plus 1. Am I right? So I'm talking about f of x plus 1 minus f of x. Okay, two adjacent pixels when we say. So you are talking about those two terms. So if I want to know what is my dou square f divided by dou x square, you have to go for an operation f double dash of x, isn't it? So in that case, the things again they will change, isn't it? But when we consider first derivative, we are talking about a difference between two adjacent pixels. So we'll see how this derivative property will help in image analysis. Okay. Uh, so those things are basic concept I have taken today, and in notes some important equations I have highlighted, and in next class some more mathematical aspect like see, you have to understand the two terms that normally you have carried out in maths, like forward difference, backward difference, and central difference. Okay, whenever we have used derivatives. Okay, try to have a glance of those mathematical aspects before attending next class. Like what do you mean by how to calculate forward difference, backward difference, and central difference in either in Laplacian or any derivatives. Okay. We'll discuss that those things in consecutive classes. But today we'll see how it will help us to understand the images. Okay, when we consider first derivative, normally it may produce thicker edges in an image. Okay, and for second derivative, we may have a strong response to fine details and noise. That is the advantage of evaluating the second derivative. And normally what happens in second derivative is you will have a sign change. Okay, sign change, and that can be used to determine transition direction in an image. Okay, so now what is this derivative is, isn't it? So what we can say is derivative is a linear operator that we are trying to compute using mask. Okay, I think mask that we have seen even in the previous content, that is especially when we dealt spatial filtering and all, we had seen mask, isn't it? But when we consider mask here, might be we are talking about Laplacian mask or some derivative mask in x direction. Okay, so value of those mask will be considered. In general, we may have a representation of a window mask. Okay, in general, we may have a representation of window mask, either 3 into 3 mask or 2 into 2 mask, like that. So if I have a window mask which is 3 into 3, obviously what is the general representation that you are aware? The center pixel is considered as W of 0, 0, and beside that exactly you have W of 0, 1, and the left side of that center pixel you have W of 0, -1. Am I right? If you go horizontal up and horizontal down row, then you have W of -1, -1, W of -1, 0, and W of -1, 1. I'm talking about the general 3 into 3 mask. Okay. And what is the bottom row related to that center pixel? It is W of 1, -1, 1, 0, and 1, 1. I hope this basic concept that you are not forgotten, that we have discussed in even filters. Okay, the filtering aspect where windowing was taken consideration. Okay, same thing we are considering here mask for the when we go for an derivative operation. So let us see now what are the three basic types of discontinuity. I'm just coming back to those two terms that we have started with the discussion, image segmentation. So we had seen there are two basic categories which deal with the properties of intensity values. One is discontinuity and second one is similarity. Okay, right now again we have to see what are the three basic types of discontinuity. One is point, the second one is line, and the third one is edges. Okay, today we'll be concentrating on point and edge, line detection, and in the next class we'll be taking the edge detection content. Are you able to understand, students? Please respond. If the things are clear, shall I go ahead?
Yes, ma'am.
Okay,
Yes,
thank
ma'am.
you. Any doubts so far? Or you felt it is fast? No? Okay. Okay, we'll see now how to deal with point detection. Though I said like I have not represented any derivative mathematical representation, but when we consider point detection, we are talking about second order derivative. Okay, so we have to go for a second order derivative, and we have to find out what are the sudden changes that is happening, okay, in the image, and that is used to detect an isolated point. Okay, so here we use an Laplacian second order derivative for the two-dimensional function. In the module 2 and 4, somewhere we had used a Laplacian kernel. Might be that time I have not discussed more into that, thinking that somewhere its connection is there in further chapters. Okay, so like I wanted to connect that Laplacian window here in image segmentation, so that understanding will be more clearer. So even before we go ahead with second derivative, how it is used to find out the point detection, I'll be taking one bit consideration where what is the Laplacian kernel and how it is used in digital image processing. Okay, right now you can remember Laplacian second order derivative is used for point detection. So this is how I was talking about the kernel. Okay, mask for the Laplacian kernel has a peculiar representation. 0, -1, 0, -1, 4, -1, 0, -1, 0. Okay. Um, how to take up. I don't know how many of your regular you are doing regular studies. Okay. Somewhere in module 2 and module 4, if you check, no, the Laplacian kernel discussion is there. Okay. So whenever such point, because we are talking about how to detect an isolated point. Okay, so always identify one threshold value and find out which are the pixel which are larger than this threshold value, and we consider them as a isolated point. So that's why the Laplacian mask or the kernel method is more useful for a detection of a line. So one application wherein how the original image may look, noise added, if it is that particular image is noise added, how it may look, and filtered output, and if it is thresholded, how the things may look like. So just to give an idea, this slide was added. Even in notes I have presented this, so that how the image will look for each stage, either with noise added, filtered output, or thresholded output. Just check here. We are talking about all those pixels available for the thresholded output. So one new term has come here, that is double effect. Okay, double effect. So how many of you have referred today's notes which I have posted, wherein I have discussed about this double line effect. Okay. So as I said, Laplacian second derivative can be used for detecting line detection aspect, but we are targeting some sudden changes or thin lines. Okay. So one more thing I have highlighted in today's presentation is regarding second derivative. It will change its sign. Okay, change its sign on line. So okay, whenever it changes sign on line, it creates a double line effect. Okay, so that's why second derivative can have negative results, and that's why we have to handle those second derivatives carefully, and we have to scale the results. Okay. So whenever there is a sign change on a line, it may create a double line effect. Okay. So what we are able to see from the picture is about the one original image. What is this original image? Are you remembering where we had studied, where we have taken this image representation? What image it is? Anybody remembers? Where I had taken this image? If you have forgotten, try to recall it. Tomorrow when we start the class, you have to tell me what is this image is and where I had taken this image, in which content while explaining I have taken this particular image. If you are remembering, now only you can tell. Yes, anybody? Any one person at least? What is this image is? In which discussion we had considered this? Anyway, try to recall it and tell me tomorrow's class kind of image it is. Okay. uh, Here the image, the first one is original image, and second image is representing a Laplacian image. And when we have an magnified section here, which is highlighted with some positive and negative double line effect here, through Laplacian image. Okay. Then third one being absolute value of the Laplacian kernel, and lastly some positive values for the Laplacian content we are able to observe for this image. Okay, we'll discuss more on this in next class. So some of the important things that you have to remember for line detection that I'm trying to take up now, that is regarding the line mask. So we speak of four different line masks. One is horizontal plus 45 degree, then vertical and minus 45 degree. How the mask values will look for each line mask. Okay. How the windowing values you have to consider when we consider it as line mask, horizontal or vertical, and plus 45 degree and minus 45 degree. And lastly, the last figure will show what is wire bond mask and what is the result after processing with minus 45 degree line mask. And if you do a thresholding, how the image will look. Okay, and that is what is represented in a given picture. Anyway, today we could analyze on two different things. That is, one is regarding point detection, and the second one was related to line detection. Okay, so what is this line detection is in overall? So it is an algorithm, okay, wherein you are trying to collect all the n edge points, okay, and find all the lines on which these edge points are lying. That is how we are trying to do in line detection. Okay, so you can say that a line is a thin segment. Okay, thin segment wherein we are observing the intensity of the background on either side of the line as much higher or lower. No, you want to check the intensity of the line pixel. And lastly, when we say isolated point, so we are talking about might be when we consider foreground pixel, the surrounding pixels are considered as background pixel, and if you consider background pixel, the surrounding pixels are considered as foreground pixel. So that's why isolated point is viewed as either foreground or background pixel. So what is the application of today's class? Okay. So we are trying to understand image segmentation methods based on detecting the sharp local changes that is happening with the intensity in the pixel value of the image.